Hello, everybody. Welcome to the first episode of Nomad Under the Hood. We'll be looking at some of the internal features of Nomad, and we have the expert with us. Uh, could you maybe introduce yourself, Michael?
Yeah, sure. Hi, everybody. My name's Michael Schurter. I'm the team lead for the Nomad Engineering team at HashiCorp. You probably have seen me online as Schmichael. Turns out there's a lot of Michaels in the tech world, so have to pick something unique, right? So yeah, good morning or afternoon.
Um, so, I was wondering, how did you end up working for the Nomad team? Could you maybe tell me something about that journey?
Yeah. Yeah, probably what led me to get started on the Nomad team was back in, I think it was 2013. Kubernetes, I think, had just come out. I think Nomad had just come out or was about to come out. Mesos was kind of the big scheduler.
I remember that
Um,
one.
People were getting out of the Hadoop world kind of and moving into more of these container schedulers. So I was working as a data engineer at this marketing automation company, and we basically had the standard data engineering problem. Had a bunch of sources to pull from, had a bunch of sinks to write to. Right, we had our own little Go system for doing that, and it ends up being and we were a little startup, so it was hundreds of these little jobs that were just reading from source, writing to a sink, from Kafka to Elasticsearch, from Elasticsearch to some third-party API, that sort of stuff. And as hundreds of little jobs became thousands of little jobs, we suddenly needed a way to manage all of them. And so we were looking around at all the different scheduling solutions, and they were all very new. I remember we were really excited about Nomad because of the no um, container requirement. If we
Yep.
were going to have thousands of these little things, each of them, I mean, just takes no resources. Some of them would sit idle for long periods of time, and to sort of ship around, multi-megabyte containers for each of these, and have all of that overhead to manage. Just didn't make sense. We needed dozens of machines running thousands of these little processes a piece, not thousands of machines running hundreds of processes a piece.
Yep.
So we were looking around, and none of the schedulers at that time really fit that need. It was going to end up being a lot of overhead. So we do what startups do. We wrote our own. NCD was pretty stable at the time, so we grabbed that as a Raft implementation. And we used just a really, I mean, to even call it a scheduling algorithm is probably going too far, but a really naive kind of work stealing algorithm for assigning work to all these workers that we now had, which basically boiled down to all of our workers would watch etcd. When a new job got posted to it, they would
Yep.
all try to claim it. Only one of them could win claiming it.
Because of
And
the locking mechanisms.
yeah, exactly. And so that one would then run off and run the workload and heartbeats that it had claimed that particular job. So if the node dies, the heartbeat stops, that disappears, the claim disappears, another worker could then pick it up.
Okay.
And so that actually worked really well, but has some like really significant deficiencies. For example, the more worker nodes you have, every time you schedule a job, all of them would perform an operation to try to claim that job against that CD. And so you just get really pathological use cases and have to do a lot of stupid little hacks to try to clean that up. But it was a great learning experience and a lot of fun. And I think they still use it to this day. So it definitely served the need
Wow.
well. But then I was really excited when an opportunity came up at HashiCorp to work on, dare I say, a real scheduler. Uh, yeah, and it's been a lot of fun.
And around what time was this? Like, what was the first Nomad release you worked on?
I think I joined around right as 04 was coming out.
Okay.
Um,
I'm
so
trying
I
to
think
remember which features those were. It's a long
I
time ago.
know. So I think 05 was Vault integration.
Yes, a vault.
Um, so we had like console integration, and the Docker driver, the raw exec, the exec drivers, those have always been there.
Yes.
Um, Rocket was still around at the time. That
Zero
was
dot
still
two
there.
was when they introduced system jobs, I think.
That sounds
Maybe,
right.
yeah, probably.
Yeah.
It's a
Yeah.
long
So
time
yeah,
ago.
yeah, it's a long time ago. Yeah, and so I've only been team lead for, oh, I don't know, probably 6 months now. So that's a fairly new role for me. Before that, just an engineer. And yeah, still try to spend as much time in code as possible.
Okay, so as one of the early people on the team, you should know most of the internals then. So we have the right person to show us through. Do you maybe want to guide us through the life of a nomad job?
Yes. Before I do that, let's make it clear that there's a lot of internals to Nomad, and so I will do my best. But I'm definitely standing on the shoulders of giants. A lot of thanks go to a lot of the design. uh, the entire design has not changed. And so that's Arman, Dadgar, Alex Dadgar. Both of them worked on Nomad from the very beginning, had a lot to do with the design. And then Preetha is now back on the console team, but while she was on the Nomad team, did a lot of work in our scheduler and Raft, and I've been pulling from her resources a lot as well. So I want to at least call out a few people who I owe a lot to for the resources and knowledge and just the existence of Nomad. But yeah, should we dive into
Yeah. Do
maybe
you?
from submitting a job?
I think that might be the interesting place to start because then eventually we will end up at the scheduler logic.
Yeah,
And it's at least a familiar place for people to start off,
yeah,
since that's
sure.
the part they usually interact with.
Yeah, yeah, exactly. Like whenever I look at a code base that I'm unfamiliar with, I usually start at the main function, right? Like
Yeah.
where's the part that I talk to, and I'll find my way through from there. So that's job submit is kind of our main function. So okay, yeah, and we'll get to I have a couple little diagrams, but we'll get to those later.
Awesome.
Um, so let's see. So the job submit. Uh, just so everybody kind of has, let's see, create job. Yeah. So when you type nomad run on the command line to run a job spec file, that ends up hitting this API endpoint. We post the new job to this V1 jobs endpoint. You can call this directly. Yeah. And so that's kind of the entry point. So let's look at the code behind that.
Okay.
Oh, so one of the first complications with Nomad for anyone who's ever kind of poked at it or looked at the internals before is that we have the HTTP API, but internally, Nomad has an RPC system. And so for the most part, the HTTP API just kind of translates to the underlying RPC system.
So is the
Um,
RPC system, is that like leveraging gRPC, or is it like separate thing?
Unfortunately, it predates gRPC.
Okay.
So it's our own thing. It's and it's kind of a combination of things. Yamix is one library that we use in there. It uses Go's net RPC package for kind of the handler setup and a lot of the plumbing. There's quite a few moving pieces. It's shared with console. A lot of these internals between Nomad and console are shared. So if you kind of know one, you'll probably kind of still feel comfortable in the other. Um, yeah, we're definitely lots of talk about gRPC. We use gRPC elsewhere, so it would definitely be fun to get on a more standard and modern RPC system in the future. We'll
Okay.
see. We'll see. But if you make a job request, as you could probably guess from this name, this is the HTTP API. So if you post that job, it hits this job update method. It comes into here, does the fun JSON decoding. One thing that constantly surprises even those of us who have worked on Nomad for a long time is you don't actually post HCL to Nomad. The HCL gets turned into JSON before it gets posted to the API.
Yes, I've run
Um,
into that many
it's
times.
it's a source of confusion. We might change that. So there's a lot of things that it would be handy to keep the HCL around for, but obviously it's also nice to not have to keep the HCL around. Whole bunch of ugly converting one external view of the struct into an internal view of the struct, just kind of boilerplate sort of code. But then here pretty quickly, you see this job register request. And you can kind of guess from that name that we're getting to the RPC layer. And sure enough, right down here, we pass things off to the RPC layer. So the HTTP endpoint is pretty small, does a little bit of validation, does a little bit of conversion, mostly just hands things right over to this RPC endpoint.
So basically just accept the job and then as quickly as possible hand it over.
Yes, exactly. And in fact, the vast majority of validation happens in the RPC and gets returned from there.
Okay.
Back through the HTTP API all the way back down to Nomad Run. So yeah, this is all still within a single HTTP request response cycle. Everything we're looking at is still within that cycle. It's just that now we're making an RPC call.
Okay.
And the fun thing about these RPC calls is this is also the layer at which we handle federation. This is the layer that we handle forwarding requests that need to talk to the leader server, making sure they end up at the leader. This has all of the fancy kind of plumbing that makes it so HTTP APIs just kind of work, no matter which node you're talking to, whether it's a server, whether it's a client. The HTTP API is the same, and as soon as we send an RPC request, it will find the right place to go.
Nice. So then it doesn't matter which server we're talking to, Nomad will make sure that it ends up at the right.
Yeah, and if you federate regions, it doesn't matter which server in the world you talk to. We'll make sure to get it to the right one. You can talk to a client in the European region and a client agent in the European region, and if that region is set for US West, it'll get routed all the way through. Okay. So yeah, I think there can be all regions have to have a direct connection to one another. And so that kind of limits the maximum number of hops we might have to take to, I forget what it is, I've counted before, somewhere around 5, okay. I think, from where you're running the command, agent, RPC, 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 and then all the way back again. It's kind of fun. It's a multi-hop system, but it's not unbounded. So yeah, so all of that is kind of just baked into our RPC system. It's not something hopefully anybody has to think about other than, wow, this is nice that I don't have to find the right server to talk to. And we start doing metrics, recording metrics for all the RPC handlers and this sort of thing. But yeah, so this is the main job registration handler.
Okay.
One thing that people might notice right off the bat is this little bit of code in here that uses some words that you might be familiar with from somewhere else. So for Nomad 010, we were adding the connect integration, the console connect integration. That's where we'll run an Envoy sidecar proxy for you. And then with Envoy and console, they'll work out all of the MTLS certificates and service discovery and all kinds of ugly plumbing nobody ever wants to think about. Hook it all up for you so service A can talk to service B, so you can manage whether or not service A should be able to talk to service B from a central place, all that fun stuff. The way that was implemented was to detect if you had a connect stanza in your job. If so, inject a sidecar in there. And the Envoy sidecar is just like any other task in Nomad. It's just an Envoy task. It's just the Envoy Docker image. That's how Envoy's officially ships their releases. So we're like, oh, there's this handy idea in Kubernetes called admission controllers for doing exactly this sort of thing, for looking at the incoming job and transforming it kind of from one form to another form. And the way that we made sure to do that is so that if you're doing like Nomad plan, or what a lot of people do will they'll pull the JSON for a job off of our APIs, change a value, and then send it back.
Yeah.
And we make sure this doesn't break that. It's not going to add duplicates, or it's not going to overwrite settings that you customize. It should do it smart enough so that you can submit it once, you can kind of tweak what it created, submit it again, and all that fun stuff.
So, are there like any ideas of what this could be used for more? Since the Connect
Yes.
integration is a great example of it, but
Yeah, it's the sort of system that is great for its flexibility, but it's also that's its greatest kind of liability or risk. And so the reason that the big kind of missing extension from our admission controllers is the ability to do them remotely. We don't let you set up a webhook or
yep.
some HTTP endpoint that will call, so you can add your own admission controllers. Um, it's one of those things, code wise, it wouldn't be hard. But the approach that we wanted to keep to with Nomad for now, we'll kind of see how things go. This is a little bit of an experiment, but we want to kind of take the Unix or even the Go kind of approach to composition when it
Okay.
comes to Nomad. So instead of creating your own admission controllers that kind of like get magically called at some weird place from an RPC mechanism, and so there's all kinds of like difficult like timing related things to think about. Instead of that, we would much rather have people wrap the Nomad API with a service, so
Okay.
that you submit your job to that. That does whatever transformations, checks, whatever, then that passes on to that. And so it's a little bit the composition approach
Yeah. More
versus,
like a preprocessor instead of.
yes, yeah. So that's kind of what we're leaning toward today. That being said, this is, obviously a powerful enough and common enough mechanism that, yeah, there's definitely lots of talk about how to extend it in the future.
Cool. Okay, so now that we have the job there and it's inside the system, it's validated. We've added
Mhm.
our connect stanza automatically to, or not the stanza, but the connect task automatically to the job. What happens next?
A whole bunch of ACL checks, but let's ignore those. ACL checks are ACL checks, right? Everybody's had to write something similar to that or run into something similar to that. So that all happens. I don't think we have to dive into that in detail. Um, but yeah, I think probably next, kind of from a functional standpoint, what we do is next we check to see if this job already exists.
Yep.
And so is this an update, or is this creating a new job? And so as we dive through code, you may see these kind of patterns and words and functions a lot. Um, Nomad has what we call a state store, and that's just kind of the core database behind Nomad. Um, and that's where the jobs live. That's where nodes live, allocations, anything that is, has an API. Just about in Nomad, that API eventually reads out of the state store.
Okay.
The state store lives on the servers. It's not something that lives on the clients. The clients, have to query from the servers to get the information they need. But you'll see over and over again, we'll grab a snapshot of the state store to work with. This kind of keeps us consistent throughout the rest of the operations that we work through.
Yep.
And then we'll operate on that snapshot by grabbing a job by its ID.
Okay. So I see memdb there. Is all that state stored in memory or is it persisted somewhere?
It is stored in memory, and memdb is, oh, that would be a wonderful under the hood to go through all on its own, because it's a wonderful, interesting little project. But it's our in-memory store. It does in-memory indexing of these data structures, and it also allows us, is involved in the snapshotting of the in-memory part to disk,
Okay.
but only for persistence. We still keep all data in memory. And we kind of chose that for two reasons, I would say. Uh, One is kind of because we can. Um, this isn't a huge amount of data.
Okay.
Even for very large clusters with tens of thousands of nodes and tens of thousands of jobs and hundreds of thousands of allocations, we're talking about gigabytes of data. We're talking about a data size that is well within what servers have the memory for
Yeah.
these days. Um, and so we have that capability, that we can do that. It's a fairly straightforward growth, or the amount of memory that Nomad uses. You can really easily track over time. So There shouldn't be any big surprises and big jumps in memory. It's like, no, as you add a node, it's a teeny tiny bit bump in memory. As you add a job, teeny tiny bump, and you can monitor that over the time, and it's fairly safe and straightforward.
And it
So
gets garbage
we
collected as well, right? When jobs get
exactly.
removed after a while.
hmm And there's tunables for all of that to kind of choose, how long you want old data to stay around versus how little memory you want to use. So yeah, we really leave that up to you to kind of control. But then the other reason is the performance benefit, is just incredible. Because not only does Nomad have its database baked in, which is already a huge performance benefit in a lot of systems, lookups like this, loading a job by ID, would be at least one remote network call to a database,
Yeah,
to an
or
etcd or some
etcd
other
or
database. Yeah, exactly. And so instead of having to go over the network, this is reading directly from memory. Instead of having to go to disk, this is reading directly from memory.
yep.
There's all kinds of times where the way we can write code in the servers is just made so much easier by the fact that it's so cheap to pull these things directly out of memory. It's not free, it's not something that you want to be redoing this work all the time, because there's still this idea of snapshotting. There's still this idea of we're having to materialize and these items, but it's pretty close to free. So yeah, it really gives us a ton of flexibility in the code we're able to write, and having that performance.
Okay.
Yeah.
So we check what is already running. Where
Mhm.
do we go from there?
Yeah, great. So we check what's already running, some more validation, check the vault policies. Oh, the vault thing is probably worth spending just a second on,
Okay.
because what's interesting is you submit when you're using our vault integration to inject secrets or a vault token into your jobs. Uh, it's there. Uh, Alex gave a great talk on it at a HashiConf, oh boy, whenever '05 came out, so years ago. But it's probably worth watching again today if you're interested, because it's a great system that's yeah, it just continues to be a lot more secure than a lot of other systems I see in this space. But you submit your job with a vault token, with your vault token, and then the policies that you want the job to have. This code just makes sure that your token has access to those policies, and then we throw your token away. We do not ever store that token. It's only used to verify that you're allowed to access the things that you're trying to access.
Nice.
Um, and then yeah, we create per allocation credentials and tokens uh, for each allocation that ends up getting created. Um, so yeah, so that's kind of a neat little thing. Let's see what else. Connect. There's some fun Connect stuff. Enforce submit job. Here we go. Finally, we're getting to kind of the next step in the chain. Raft. So this code right here is where we're actually taking this job that you have submitted and committing it to Raft.
Okay. So this
Go
will
ahead.
actually like effectuate the new version of the job.
Yes, exactly. So Raft, for those not aware, is a consensus protocol. Um, etcd implements it and uses it, and Nomad implements it and uses it. Console does, Vault does now as well. A whole bunch of other projects do too. Um, what it does for us is ensures that your Nomad servers, and so when I say servers, Nomad uses that term in a little bit of a confusing way, but I'll always mean it to be your Nomad agents running in server mode. So that means you have that server stanza with enabled equals true in it. Um, so all of those are participating in Raft, and there's tons of great websites and resources if you want to learn about Raft. I won't get into that. Super interesting, super well documented, a lot of fun to learn about.
We can link
Um,
them in the video notes.
yeah, that's a great idea. Um, but yeah, long story short, it's so all of the Nomad servers uh, agree on the operations being applied. at the end of the day, that is what Raft does for us. Is it ensures when we say commit this job to the Nomad servers, either all the servers or a quorum of the servers either say yes, great, I got it, or they say no, I don't, and things blow up, and you get an error message back.
Yep.
Uh, so it's a big, huge, complicated system that all it does is make sure something either definitely does happen or definitely does not happen, and there is no fuzzy in between.
So with Nomad, does Nomad also have the concept of non-voting servers, or?
It does, yeah. Yeah. Since Raft, since all operations, for the most part, pass through Raft, it's obviously very performance sensitive. You'll see later on in this code, we're going to talk to Raft another time. So every time you submit a job, there are at least 2 Raft operations involved. Um, so it's very performance critical. Raft is what writes to that state store that we saw above, the
Yep.
memdb. And so everything that it does, it writes the log of operations to disk before applying them to the state store. So we do write to disk for safety, durability, persistence. Um, but otherwise, it operates mostly in memory.
So
It's
the
not
things that write to
reading off
disk
of
is
disk.
like the standard write ahead log.
Exactly.
Okay.
Exactly. Yeah, my coworker Mahmood on the Nomad team here actually just we had a hack week recently, and he just rewrote a more efficient write ahead log for a hack week, like you do. And I say hack week, and it was actually just 3 days. So this stuff is really fun to play with. I have to be honest. It could get confusing to find your way around it, but once you do, like, you can rip out whole chunks of code and replace them with something new fairly easily. It's pretty fun. But yeah, all that to be said is, yep, write ahead log to disk. All operations then are kind of in memory from there. Um, and that's what Raft does for us. And in fact, all this does is splat this job into the database, into that state store in memory database. We still haven't even gotten to the point where any actual scheduling takes place.
Yeah.
At
So
this
so this
point,
is just choosing what the job looks like
yep,
in memory.
yep,
Okay.
exactly, exactly. Um,
So where do
but
we
now
go?
we've saved it to memory.
Yep.
Uh, so we have it. So we can go down. There's some fun stuff around periodic jobs. We could ignore those for now.
The
Um,
evaluation part looks interesting.
yeah, this is where it gets
I
really
remember that from
interesting.
the CLI. So
Yes, yes. Evaluations are kind of a tricky thing because on the one hand, they're an internal implementation detail that hopefully you don't have to know very much about. On the other hand, they are probably the most critical internal implementation detail. And so we do want to expose you to them because they're handy for so many debugging operations to kind of know what's going on in the background. Um, and yeah, it's one of those things that hopefully you don't have to worry about. But if you do have to worry about, we want to make it easy for you to start poking at them, read them, uh, and that sort of thing. Yeah, what is an evaluation? I should probably talk about that, right? So we're creating an evaluation at this point. I wonder, yeah. So if you go to nomadproject.io, these scheduling internal stocks, Eric and I were talking about, they need a refresh. They're pretty old at this point, but they're still true. They're still accurate. Uh, we just have more designers and things like that on staff that could do a much better job, I think, at clarifying a lot of this visually. But anyway, evaluation right up there up front. One of the first nouns that we mentioned on this scheduling internals page. So if we kind of scroll down to this image, this path is, what we're going through. Oh dear. And it's taken us 30 minutes to, talk about just this arrow. I'm sorry. There might be a lot going on. But yeah, so now we've created an evaluation. So what is this evaluation? Evaluations are created from any event that could cause a scheduling action to be taken. So it is kind of the main unit of scheduling, or the edge trigger to cause scheduling, is
Just like
probably the best way to put
any
it.
change in state, right?
Yes, exactly. So job register, that's the most obvious one probably. Updating the job, same thing. But also node failures. So this is the same mechanism if your node, if your Nomad client agent dies, if the VM blows up, if the bare metal catches fire, um, that lost state that your node gets marked as because it failed to heartbeat. Nomad, the servers notice that, they mark it as lost, and then they emit an evaluation for that node saying this node is gone, figure out what to do about it.
Okay.
And the evaluation is that event, that node failure event. uh, so yeah, so this is kind of a sneak peek at where we're going from here, but yeah, these evaluations go into a broker. And so this is really a queue that Nomad has internally.
Okay.
The broker, like this says, is only on the leader. uh, Raft is what gives us that leader. Raft gives us leader election as well. So the leader of the Raft quorum is the one that has kind of the queue of evaluations that need to get processed. And this is where things get really interesting, is that then all of the other servers uh, can pull evaluations out of that queue and try to schedule them.
Okay.
And this, and it's not clear from this diagram, and probably because this diagram already has plenty going on,
Yes.
but this part up top, where we actually create the evaluations, and you can see this in code right down here. This, the evaluation is committed to Raft. So that's that second Raft operation I was talking about for
Yep.
submitting a job. But once we commit that to Raft, this queue, this dequeuing, and all of this stuff down below is outside of Raft.
Okay. So that's all in memory again.
Exactly. And it's all using that RPC mechanism again that
Okay.
we talked about toward the beginning for getting the job to the service to begin with. So yeah, this is kind of a huge design decision in Nomad, and kind of the probably the core design decision around the performance of Nomad scheduling. Being in memory helps a ton. Not having to make remote calls to get data helps a ton. But this really ensures the scalability of our scheduler, because it means each server in your cluster of Nomad servers is able to help out scheduling jobs. And so this is called optimistic concurrency, because the idea is that they're all working in parallel. If you submit 10 jobs with 100 count each, and so we're having to submit, having to create 1,000 allocations total, all of that can happen in parallel, which means they might conflict with one another. We might say, okay, job A, we're going to put one of your allocations on node A, or node 1. Job B, we're going to put one of your allocations on node 1. Those two decisions might be made in parallel and might make it so that node 1 gets too much work.
Yep.
Because they're working in parallel. This is outside of Raft. They're not having to wait on one another and work in lockstep. And so once these optimistic scheduling decisions are made, they create what we call a plan. The plan goes into another queue, and the leader does the serialization of the plans. So it takes one at a time. It says, is this valid or not? If it's valid, we apply it. Is the next one valid? If it's valid, apply it. Is it valid? So the leader still ensures that we don't over provision a node.
Okay.
It ensures that even if we schedule, a million things concurrently, they all conflict with each other. We're only going to accept the first one. All the other ones get booted back and they get tried again.
So in like the most simple version of this, if you only had one server, then basically it is you have a queue of incoming work. The scheduler then looks at it and then puts it in the queue of like, these are ready to be processed. Is that
Yes.
like the most simple
Yes.
version?
Yep.
Okay.
Yep. So even if you're running the dev agent, all of these internals are still exactly the same.
Okay.
There's still internally an evaluation broker, just doesn't go over a network. It just talks to the workers internally. So I'm probably going to accidentally say the word worker a lot. So I should explain what that is. Workers are a component of servers in Nomad. There's a worker.go. Let's just hop over to worker.go. So let's see, worker. So there's a worker.go. This is a component that runs within the servers, and it's a single scheduling thread. Yeah, the comment here is pretty good. Yeah, the comment's really good. The next sentence is really key too. There may be multiple running per server. So we actually look at the number of cores you have on a server because this is a very CPU bound operation because we have all the data we need is in memory. So then, the expensive part is just acting on
Processing
that data.
it.
Yeah, exactly. And so we parallelize it based on the number of cores. We try not to use all of your cores. You can dig around for that exact calculation somewhere. You can also tweak this setting in the agent config. Yada, yada, yada. Worker is an internal component, single threaded, does the actual scheduling work. So even if you're running just a dev agent, there's still this internal queue of evaluations. There's still probably multiple worker threads that could schedule in parallel with one another. So even if you run a single server, we're still working, doing scheduling concurrently.
Okay. So like very simplified view of that again is basically that even though you have 3 servers, you might have like multiples of those actually like scheduling, right? Like as cores, you could have 4 cores per server scheduling, giving you 12 schedulers.
Yeah, exactly.
Okay.
Exactly. And so it really gives you a lot of options for scaling. In general, people see larger Raft quorums, like say you have 5 servers or
Yep.
7 servers in your Raft quorum. You take a little bit of a performance hit there because we need to ensure that the data is committed to a quorum of those nodes every time.
Yep.
So that is still true in Nomad, but each of those servers does get to participate in this scheduling as well. So, we kind of make up for that performance loss. You can kind of think of it this way a little bit: make up for that performance loss a little bit by having more cores to schedule across.
Okay.
Yeah, so Nomad has some really interesting scaling properties, I think is the short version of that when it comes to servers. But we really want to make it so that we take advantage of the hardware you give it and can scale up to very large or very busy clusters.
Okay. So what does one of those workers do internally?
Yeah, great question. Let's see. Let's quick head back to the job endpoint because we'll get there right now. Actually, we're done with the job endpoint. Applying that Raft, committing the evaluation to Raft is the end of this job endpoint. Yeah, like you were saying, you'll probably notice that in the CLI is you get that evaluation ID back.
Yep.
And the CLI actually will wait around a little bit to see if it can give you another kind of status update about if the evaluation gets applied really quickly, and it will give you an allocation ID.
Yes.
But what is it? There's a detach flag. I forget what the flag is to make it just the CLI exit as soon as this evaluation is committed, and it's kind of up to you to track the evaluation from there.
Okay.
So yeah, long story short, this is the end of the job submit RPC. This is the end of the job submit HTTP API. So if you are talking directly to the API instead of using Nomad Run, then you get a response as soon as that evaluation is created. One of the I've created so many helper functions around this over time when writing tests and other little tools. But yeah, the next thing, if you're working at a really low level with job submitting, is you submit the job. If that comes back successful, then you do a blocking HTTP query on the evaluation.
Yep.
And as soon as that evaluation completes, then you can, look up the allocations for that job, blah, 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 blah. All of that kind of is what we're stepping through, one teeny tiny step at a time. We have finally gotten to the evaluation part, and now we'll see how we get to the allocation part after that.
Cool.
But the problem is especially if you're digging into this code, and this is a hard part for us as engineers to kind of learn for the first time, for the fifth time sometimes. Um, but you're kind of stuck if you're just trying to dig through code from here because okay, so we put an evaluation in Raft, but
Yeah.
now this
There's
is
no
just
thread to
done.
pull.
Yeah, where do we go from here? You know, you're tempted to use jump to definition in your editor to dig deeper, and it's like, well, okay, now we're digging deeper into Raft, but this is not useful. This is all very low level Raft code on how we apply Raft operations, and has nothing to do with evaluations or scheduling. So this is not useful. So what happens from there? And what happens from there is that Zoom is in my way. Get out of here, Zoom. Okay.
That never
What
happens to
happens?
me.
Yeah, right. Oh no, I usually end up in annotation mode accidentally when I start moving Zoom things around. Start drawing on the screen. Let's see if I can avoid that. Where did our evaluation go? That's where we're at. And where our evaluation went is to that broker. And so inside the Nomad package, uh, we have a file called evalbroker.go, and it is this code right here. So
Okay.
like I said before, this is only running on the server. There's only one of these brokers, and it's the queue that evaluation's getting queued in.
And that's
And
also
then
single threaded, then I assume.
correct.
Okay.
And then it is the yeah, and then workers DQ the information in there. Yes, and there's a near infinite level of details and subtleties that we could actually go into this. I mean, even just kind of where we ended up, there's knacks involved as far as explicitly not acknowledging an evaluation being run. One of the big complexities that the evaluation broker has to work with is blocked evaluations. So if we can't schedule a job,
Yeah.
a blocked evaluation gets created, and that sits around waiting for anything to change that might unblock it. So there's all kinds of plumbing and subtleties involved in that. But the basic idea is say you try to run a job that requires Windows,
Yes.
but you only have Linux nodes. That blocked evaluation is going to get created, and that it'll just sit around waiting. As soon as you spin up a Windows node, we'll notice, in this diagram, we only say node updates. Oh, I have a more complete diagram. Thanks to Preetha for this fantastically detailed diagram. Let's see, node updates. When you spin up that Windows node, it creates a node update.
Okay.
That gets sent to the eval broker. It notices, oh, hey, we have a node now that might satisfy one of these blocked evaluations needs. Let's unblock that evaluation.
So is
This
that
gets
a separate queue where it keeps the block evaluations and then puts them back into the main queue so they can get picked up, or?
yes,
Okay.
yes. And yeah, there's some fun optimizations in there to make the unblocking and blocking efficient. We definitely don't have time for those today. But yeah. Point being is we'll unblock things. Maybe even a more common case is just if you don't have the memory or CPU available in your cluster to schedule a job.
Yep.
That's a blocked evaluation. That'll wait for another node to come up, or that'll wait for if a running allocation gets stopped. That's another scheduling event, and that will cause things to get scheduled again.
Okay.
So yeah, you have all of these ways that things can get scheduled or that can cause scheduling to happen.
So
Um,
that
yeah.
queue, is that so the evaluation got applied to Raft. Now, how does the worker constantly check Raft to see if there's updates? Or how does it get triggered into putting things into its queue?
Yeah, good question. Let's go back to worker.go. So worker.go is or the worker struct inside of it just kind of has a long-lived go routine. This is our single scheduling thread right here. This run method is that single scheduling thread. And it just dequeues evaluations. Our RPC mechanism has an idea of blocking requests. And so your blocking HTTP query turns into a blocking RPC query, and the entire system, kind of works in coordination like that. So we also use these blocking, you can kind of see this comment right down here. We also use those blocking RPCs internally for these evaluations. So this RPC is not a public API. You should not be trying to DQ evaluations to try to schedule by hand. No, this is for the servers, but it's the same RPC mechanism. We get to kind of reuse that plumbing. And it just
Okay.
does a blocking query, a lot like any sort of work queue that you're probably used to. Uh, yeah, so I don't think there's anything particularly interesting when dequeuing it, but if we go back to where that happens, so again, now we're back in, this is that main scheduling loop.
Yep.
This blocks until, either it's told to shut down or until we get back an evaluation.
Yep.
And once we get back an evaluation, I told you would see this again. The code does look a little bit different.
Snapshots.
But
Yep.
yeah, we snapshot that in-memory data, that in-memory database, that memdb. The great thing about memdb is it makes snapshots almost free. And so we take a snapshot of it. And the reason we do that is because we want all of the decisions we make when scheduling this evaluation to be coherent. They should have the same view of your cluster. The interesting thing to keep in mind is all of this happens concurrently. We're outside of Raft right now, even though we're pulling things out of this state store that is written by Raft. This evaluation may have been created 1,000 Raft operations ago.
Okay.
And a lot of stuff could have happened in the meantime. And so this snapshot that we're getting could represent, this entirely new view of the world. But we want to make sure that we use a consistent view of the world when actually making scheduling decisions. So that's why we take a snapshot. That min index thing is actually, yeah, it's a little bit interesting because, like I said, since everything is kind of running concurrently, we kind of have all of these consistency checks that we need to do, or rather, consistency invariants we need to enforce. And so this one, oh yeah, has a big comment. Yeah, this one is pretty interesting because what it wants to ensure is that the view of the world, the view of the cluster state that we're going to use for scheduling decisions is at least as new as when the evaluation was created.
So we're not going back in time and applying things
Exactly.
that are not valid anymore.
Exactly. There's all kinds of funny time travel problems that you run into when you have massively concurrent systems like this, when everything can happen in parallel. Because the only real alternative to that would be to make everything move in lockstep.
Which
The
would slow
jobs.
down everything and you lose all the benefits of
Exactly.
concurrency.
Exactly. It would be unbearably slow for relatively, for even in relatively low throughput clusters, small clusters. It would be extremely slow to say, okay, as long as we're operating on this job submit Raft entry, all work has to stop. We're not processing node updates. We're not processing heartbeats. We're not processing other job submits. We're going to take this job, pause the world, schedule it, and then unpause the world.
Yeah.
Is
Freeze the
just
world moments are not great.
yeah, exactly. And so once you give that up, you're stuck with having to ensure all of this correctness kind of on your own. So it gets complicated, but the nice thing is it's a linear view of the world that we have, right?
Yep.
Everyone's probably seen that index that gets added to jobs about when they were created, when they were modified.
Yeah.
Raft ensures, the uniqueness of that index. That index only moves forward in time. So even though it seems like a really complicated operation to say, okay, snapshot, to make sure that the state of the world is past this state of the world, it's like that's comparing integers. It's not, a hard operation to do.
It's just checking the time, basically.
Yeah. So, okay, we're we're almost to the end of our time, and we've actually made it to scheduling.
Yes.
Um, so as you can probably guess by this method name of it, invoke scheduler, we're finally getting to where scheduler decisions are made. I'll try to get to the fun parts here as quickly as possible. Um, but one interesting little diversion, really quickly, is that we have multiple scheduler types. One of them is a core type that's totally internal to Nomad, and we actually use the scheduler to perform maintenance tasks on the scheduler. And so
Okay.
that's things like garbage collection
Yep.
of old jobs or old nodes is a job that gets run through the scheduler. It's assigned to a node to perform, or not to a client agent to perform, but to a specific worker, server worker to perform. So we even tried to parallelize that work.
Nice.
Um,
So
yeah,
so Nomad basically uses its own architecture to do its own internal scheduling and
exactly.
functioning. That's
And
cool.
that you see a lot. Yeah, we reuse the RPC mechanism, both kind of for the public API as well for internal APIs. We reuse the scheduling kind of pipeline, not only for all of the work that we do on user jobs, but also for these internal jobs. Yeah, yeah. But for the most part, everyone cares about this new scheduler. And we have two main types of schedulers in Nomad internally. One is for system jobs, and one is for batch and service jobs. System jobs are the jobs that run on all nodes, or at least all nodes, that meet the constraints, basically.
Yep.
Um, and then service jobs are kind of the more common ones that everybody is hopefully familiar with. Run 5 Redis servers, that sort of thing.
Run my
Uh,
batch job.
yeah, and then batch jobs are similar enough that they use most of the same scheduling logic, so they use the same scheduler internally.
Okay.
They have a few optimizations because that make their scheduling a little higher performance, but not bin pack as well. And we'll
Okay.
get to that in more detail hopefully here, but the gist of it is that we want to bin pack services as well as possible
Like
in
Tetris.
order, yes, in order to use as few servers as possible and save everybody money is the goal here. Batch jobs, we want to do that, but the idea is that we want to err a little more on the performance side with batch jobs, and especially because they're short-lived
Yeah, get them
or
out of the
shorter
way
lived than
as
service jobs.
quick as possible.
It's not as important to get them bin packed perfectly. It's like, no, they're going to go away soon anyway. Who cares? Just get them somewhere, get their work done, get them out of here. So they have a little more high performance route.
All right.
Uh, we go off to process the evaluation. So this is using a Go interface. Like I said, to have those multiple scheduler implementations. Uh,
I think the service one is probably the most interesting
yep.
to look at, right? Since the system is more checking which hosts are valid and then puts them there.
Yes. Yes. Exactly. So here's that process implementation. So now this is where your job submit evaluation has ended up. If it's for a service job or a batch job, it will end up in this code. We do a little checking. So here's like a great list of evaluations that could trigger this sort of event.
Yeah.
So
That's
this
the same
diagram
ones.
is,
Yeah.
yeah, right
In
here.
Preethos diagram.
That's these, and then some more internal ones that we didn't cover in that diagram. Little boilerplate that we can ignore. Here we go again, looking up our job ID. Job
Okay.
ID, loading this. Uh, an interesting optimization that this kind of points out here is that when we created the evaluation, we had this job.
Yes.
Why not just pass it along with the evaluation? Why do we look it up again? And the reason for that is it's actually way cheaper to look it up again than it is to pass it along with the evaluation. The
Okay.
evaluation is sent over the network. That means it has to be serialized. It uses
Oh,
up your bandwidth,
deserialized.
deserialized. If we put the whole job in there, some people have large jobs. That's just extra work to do. Because the job is already committed to Raft,
Yep.
all the servers have it in memory. There's no need to serialize and deserialize it. There's no need to pass it across the network. So a big optimization that we did from the beginning and then made sure to extend it to a lot of places over time is to normalize a lot of the things that we pass across the RPC to ensure that we're not passing things that are already in memory on the remote node anyway.
Nice.
If all the servers know about the jobs, so don't reserialize the jobs all the time. Yeah, so that's a very significant performance improvement for a lot of use cases. You can imagine if you have a job that say creates 1,000 allocations, the
Yeah.
group count is 1,000.
Having to send all of those to all the
It would
servers or
send
clients.
1,000 copies of the job if we didn't do this optimization, across your network, and just uselessly. So that's one of those small decisions that has a huge impact. Let's see. So I want to make sure we get to the actual interesting, the actual bin pack algorithm, because that's kind of what everybody thinks about as a scheduler. It turns out that most of the work a scheduler does is boilerplate around that. But let's see. We're coming in here. We're checking about whether we can do updates in place or not. I
Oh,
don't
so
know.
that means do we need to create a new allocation, or can we just update the existing?
Exactly. That's
Okay.
all happening in here. And so all of this, you'll see the word plan a lot. The worker gets an evaluation and creates a plan.
So
And
does
so
it
the
do that
plan,
immediately? Like as soon as it gets an evaluation, create a plan and then alter that
yes.
plan along the way?
And that plan is not in Raft. It's purely something in this worker, in this single threaded worker that it's creating, and it has things like create these allocations, stop these allocations.
Okay.
It's all the actions to take based on that. Oh yeah, you can kind of see, append stopped allocations to the plan.
Yeah.
You can kind of see those operations here. So let's see.
So it
Here we
basically
go.
like constructs the plan step by step and then builds it out.
Yes. Yes. So let's in my rush, I'm not seeing where we jump into this next step, but let's just
Don't
jump into
worry,
the.
you don't have to rush. It's not a problem if we go slightly over. I'd rather
Okay.
us show all the awesome things that you have to show.
Okay. So this generic stack, and so now I'm in the scheduler package inside Nomad, if you're following along.
Okay, so how
Most,
did we get here from the worker into
yeah,
this? Just so
that's
we
what I was.
don't lose track of where we are.
Oh, but I lost track of where I am. A val broker, we passed you up. We don't
Yep.
need the FSM.
We
We'll
were in
skip
that
that
place
today.
where you were looking like add stopped jobs, handle things that could not be placed.
Generic scheduler.
Yeah, we were in the internal function of process.
Yeah, let's see. Compute job, Alex. Where do we call? Yeah, here we go. Select next option. Okay, great. I can find my way from here. So compute placements is called by compute job Alex, which is called by process.
Yes, this is where I
Lowercase p
remember
process. Yes.
we were
Okay.
making a plan. So we have an empty plan.
And eventually, we have an empty plan, but we have an evaluation. So now what we do is we create what we call a stack. And generic, and the generic stack is for the generic scheduler, meaning service and batch jobs. System jobs get a simpler scheduler that just needs to evaluate feasibility, more or less. Can a job fit on a node? If so, great, put it there.
So does it first put all the nodes in, or like all the possibilities in, and take out possibilities that don't fit, or the other way around?
Great question. So that is exactly what we'll get to right now. So we create this new generic scheduler stack, and we set the job on it.
Yep.
And then this compute allocations is what kind of like kicks off everything that we're about to look at.
Okay.
So this is that new generic scheduler stack. And so what this is setting up is a stack of iterators to iterate through all of the nodes in your cluster
Yep.
to evaluate their fitness for this job.
Okay.
Except we don't want to go through all of the nodes in your cluster. So there's a lot of performance related decisions in here to try to make sure we do as little work as possible
To get
and
it
still,
scheduled as quickly as possible.
yes, exactly,
Makes
and
sense.
still arrive at a correct result.
So I think something very important what you just said is to determine fitness, because I think that's a term that we'll hear more as well. Can you maybe explain that like shortly?
Yeah. So there's kind of two major stages to this part of the scheduler, to actually scheduling a job onto nodes. There's kind of two phases to it, and one is that feasibility. Is it at all possible for this job to run on this node? So we have our Windows job. It requires 1 GB of RAM. If we look at a Linux node, that's just a
Yeah,
no.
never gonna work.
Nothing else matters. Yeah. We have some fun optimizations for things like that. That's called a computed node. Oh, class. Computed node class is if you run into that, it's a fun optimization to make that really cheap.
Okay.
But then you have things like, is there enough memory? We found a Windows node. Does it have a gigabyte free of memory? That's also a feasibility check.
Okay.
So
But
first
is
things
that
we
memory on the machine or memory available at that time?
that is memory. Oh, that's a great question. So one thing that really I feel like we have to clarify a lot, because it's not always immediately intuitive, is that the scheduler has kind of a static view of the nodes that it's scheduling on. So if your
Okay.
node starts up and it has 8 GB of RAM, it tells the scheduler, I have 8 GB of RAM, and the scheduler records that node update.
Yep.
Now you might manually start a service on that node. You might manually stop a service on that node. You might, be installing updates on that node. Those all affect the actual amount of memory available.
Yep.
That does not get sent to the servers, so that does not impact scheduling.
Okay.
So it is not a live view of nodes,
It's
just because
a view from the node started, snapshot.
Yep.
That's the view. Okay.
And so then if it had 8 GB when it started and we schedule, 1 GB worth of services on it, the server just does that math. It does that
Okay.
accounting. It doesn't look, did you actually use 1 GB or not? Doesn't care. It just does the math on the servers.
Okay.
So that node has 7 GB left. Then it has 6 GB left as the next service gets scheduled, and so on. So that keeps the scheduler making the most conservative decisions.
Yeah.
It's not being over ambitious here and trying to over provision nodes. There's other ways we want to accomplish that and do that. But for the scheduler's perspective, it just does the math. That keeps the reasoning about what the scheduler is doing way simpler. And it also obviously has massive performance improvements versus if we were trying to gather live statistics from all of the nodes in your cluster to make these schedules, not only would the performance be terrible, but it would be incoherent.
Yeah.
Those
It
numbers
would change every
too
time
quickly.
and
Yeah.
recompute every time. Makes
So
sense.
all we can really do is work off that more or less static view of the world.
Okay.
So that's feasibility.
Yep.
Just making
So
sure.
we're taking out the hosts that are not feasible.
Yep. And that's kind of what all of these parts of the iterators at the top part of the stack are doing,
Okay.
is doing constraint checks, checking to see if your driver is running on that node.
So it's basically
CSI,
trying to filter out as many nodes as possible
exactly.
before it starts with the more difficult scheduling task.
Exactly, because these are super easy checks to make, just easy comparisons, that sort of thing. So it does lots and lots and lots of feasibility checking. The further down we go gets to like the more expensive kind of checking. So we have
Right.
things like distinct properties and distinct host constraints. These get a little more complicated because they're for spreading allocations for a job across multiple hosts and or hosts based on properties. And
Yep.
so there's kind of more interdependencies and it gets a little more complicated. But then once we get past feasibility, you can see an upgrade from feasible to rank. And so this is where we now get into more of the fitness scoring as opposed to the Boolean, would it work at all or not?
Yep.
And so right off the bat, you can see the bin packing scheduler. That is probably what we've all heard about, team talks about, that sort of thing. And so it finally makes its appearance. Uh, and we can it's so small that we can just like super quickly hop in here and you can actually see it. We just added this, by the way. We now support switching your cluster wide scheduling algorithm from bin packing to spread. It's cluster wide right now. We're gonna play with this probably in the future, but the idea here is we have lots of users on bare metal. There's no point in bin packing if you're still going to be running 100 machines, even if you only have 10 machines actually utilized. So we wanted to create this spread cluster-wide switch to make it so we use all 100 of your bare metal machines that are going to be on either way. We're not going to save you money. We're not going to save you electricity by bin packing. So let's spread it all out. So
Okay.
that's available now in 0.11.2 that was just released. And look for more improvements to kind of it in the future.
Cool.
Uh, but oh right, that means that this is now configurable. So this is the bin packing algorithm. This is what so many talks have been given about, and this is how much code it fits into.
That's amazing.
Uh, yeah,
20 lines.
yeah, yeah. So it basically tries to maximize the tightest fit. So the highest score is if you have 1 GB of memory free and 1 GHz of CPU free, and you have a job that needs exactly that, that is going to be a 1.0 score. That is going to be a perfect score. You don't get any better bin pack than that. If it's going to leave a little bit of space free, that's going to be a close to 1 score, but
Yep.
not as good. And if it leaves tons and tons of space for you, that's going to be a very poor score. That's how bin packing works. It's all based on this PowerPoint. If you peek above, no, this is just doing the math for figuring out the free. Where's the spread? Here's spread. So spread is even simpler. It just kind of inverts that logic. Instead of saying what's the tightest fit, it says what's the worst fit, which is kind of you don't often see the word worst used to describe something that you want, but that's what you want when you spread. You want the worst fit. So you don't want to have the tightest fit. You want to have the most extra resources available after this is done scheduling. So this is it. That's the scoring algorithms.
And I believe in that PowerPoint, they also explain more like why you would want certain algorithms, right? Because you could do spread with random, but it would end up being less spreaded than the worst fit was, right? If I recall correctly.
Yes, exactly. Exactly. Oh shoot, I even have a PDF of that thing available somewhere, but who knows?
We'll
No
link it in
time for that
the
now. But yeah,
description.
yeah, exactly. But yeah, so we are here right now.
Yeah. So we now found um, the hosts like with the best fit, right? And that will be put into the plan.
Yes. We
Okay.
we we
So
scored them. We figured out who has the best score. We chose them. We put that into the plan. And so this is all for figuring out which node to put an allocation on.
okay.
And so if you have, count 100, we've gone through this 100 times to figure out, where to put each allocation. All of that gets put into a single plan.
Yeah.
Oh, so one kind of really quickly important performance consideration is jobs are scheduled as a unit.
Okay,
We
because I was
don't,
going to ask you that. Like, what if I
yeah,
have multiple counts in my group? Do they end up at one scheduler to make that decision?
Yes.
Okay.
Yes. Yeah, exactly. So you should kind of that is one consideration when considering like, oh, do I want to do multiple task groups within a job or multiple jobs? I mean, jobs are the unit of scheduling, and then allocations are kind of the unit of placement.
Okay.
Uh,
Makes
and so
sense.
this plan will contain all of the allocation changes
For one job.
for that job that just got
Okay.
scheduled. Right. That gets sent back to the leader.
Via the same RPC mechanism?
Exactly. Exactly.
And then the
So
leader
yeah,
puts it in the queue for the
the
plan queue?
leader, it gets put into a plan queue on the leader.
Okay.
The leader pulls off one plan at a time. So this is where we do move in lockstep.
Yep.
Uh Pulls off one plan at a time and just does that final quick validity check. It's like, okay, is this wants to schedule Alex A, B, and C on
Yep.
nodes 1, 2, and 3. Is that still valid at all? It is. Great. Place them.
So does the
Yeah.
leader then go through the same feasibility and fitness check as the other schedulers went through? Or like how does it check if the
Yeah.
plan that it got given is still possible?
Yeah, so this is back in the Nomad package again. The Nomad package within the Nomad repository is the server. It's poorly named. I'm sorry to everyone, but yeah, for historical reasons, the Nomad package is where you should go for all of your scheduler kind of entry points. Um, but yeah, so the plan applier is in this plan apply file within the Nomad package. Um, has some ugly checks. Let's see if I can get to the nuts and bolts of it though quickly. A lot of those checks had to do with the denormalization, normalization that I kind of talked about earlier. Those optimizations.
Yep.
Um, Preempted jobs. Oh yeah, preemption has a huge impact on all of this because we might be causing more scheduler work by finishing the scheduler work if we're preempting work. So that has a huge impact here. Um, oh yeah, but here's an important place where at this point we've actually applied the plan results to Raft.
But that's after the check if it could apply the plan, right?
Yes, that is what I'm still looking for. Oh yeah, this is too low level.
Oh, we need to move up.
Yeah, going up to plan up. It's a plan apply function that calls an apply plan method. Yeah, naming things is hard. Yes, here we go. Evaluate plan. This is what I was looking for. Is used to determine what portions of a plan can be applied, if any.
Okay.
Oh, so there's even so it can even be a sort of thing where it's like, okay, 8 out of the 10 allocations included in this plan work out great. Let's
Yep.
schedule them. Let's get them working. But you know what? Those last two, they're going to have to be rescheduled. The
I've
plan
seen that
applier,
before. Like if
yeah,
there's not enough resources to put all of them, but maybe like most of them can get placed.
yep, yep. So here we do kind of a stripped down version of the feasibility checks we did elsewhere.
Okay.
So if you see above, it'll check quotas. If you're using quotas in Nomad Enterprise, um, it'll check. Let's see, where is the actual fitness function? Add this plan to the results. That handles the results.
Evaluate each node in the plan. That sounds. It was slightly higher.
Okay. Handling results is that. Oh yeah. No. Oh, what's on the other side of this channel? See, we do parallelize everything all the time. Oh boy.
Well, if you can't find the piece of code, do you know like somewhat what it checks?
Oh boy. I mean, there's still quite a bit. Here's a great example. Ensures that deployment object doesn't list any canaries as placed if they didn't actually get placed. Lots of little correctness checks.
Okay.
The reason why it's why the leader can do this quickly and easily and efficiently is because it has all of the information it needs materialized right here. It's not iterating through every single node in the cluster.
It
It's not
has the source
having
of truth.
Yes, it's not having to check to see if preemptions are available. There's a lot of work that the workers do to try to figure out if a preemption would change things. It has all of that done, and so it's these very static checks
Okay.
against, from a plan against a node, and it has the allocation in the node right here. So shoot, I'm sad I can't find the entry point, but that's why it is cheap, is because it has all of the information it needs. No iteration, no searching, no having to score or evaluate fitness, reorder. Yep, all that's done. And if it's not done, if it fails, that's an evaluation. Kick off a new evaluation, cause all of this to happen all over again, and hopefully it'll work this time around.
So if the plan fails, it goes all the way back to the top of the chain.
Um, yes.
Okay.
I think there are some subtle,
Caveats.
yes.
Okay.
Oh boy, yeah, there's all kinds of fun, subtle caveats. But yes, in general, that's the right way to think about it.
Okay.
Yeah, there's fun stuff in here, like you'll see this refresh index, not a created index, not a modified index. This refresh index is useful for a particular time travel problem where the the plan was created against an old view of the world,
Okay.
but was verified against a newer view of the world. So when trying and when it was verified against that new view of the world, things had changed.
Yeah.
Nodes had disappeared, whatever. Now that plan's not valid anymore. We want to make sure that when we try to create a new plan, we don't just create it against an old view of the world again. We know that's not going to work. We know that's going to get rejected. So this refresh index is the hint to the next scheduler, to the
Yeah.
next worker doing the scheduling. Okay, make sure you're at least at this point, otherwise you're just going to fail again.
Makes sense.
So we have all kinds of little hints and things like that in here. But yeah, in general, evaluations, yep, we'll just get kicked back into the queue, back through the worker pipeline. The plan will get enqueued here and hopefully applied again.
And what if we have a successful plan? How does it then become an allocation? Is that just an RPC call or?
Yeah, that's a great question. So the plan includes the allocations to be applied to Raft. So the plan, will say create 10 allocations, update. Say it's a deployment,
Yep.
and you're creating 10 new allocations, and so you're stopping 10 old allocations. It will, in Raft commit, it can say, okay, change the desired status of the old allocations to stop and create these two and new allocations. And then clients are just doing blocking RPC calls to watch for allocation changes that they care about.
Okay.
So there's an RPC for clients to say, I'm node foo. Tell me when anything changes for allocations on node foo.
Okay.
And
So
so
it doesn't care about anything about evaluations or just
correct.
I have allocations assigned to me if anything in those allocations changes or I get new ones.
Correct. Clients really only just get these lists of allocations that they're responsible for. That's the only thing that they really deal with. At the point they get allocations, we put the job back onto it because they
Yep.
need data out of the job. But yeah, for the most part, clients don't know anything about evaluations. Anything related to looking up evaluations, any APIs around that get forwarded to servers. Yep. So by the time you get to a client, they're just client. There's a component within clients called allocation runner, and it's
Yep.
kind of the core component. And basically, all of the other code in the client is just to get allocations from the server and give them to allocation runners. And so we actually kick around the idea a lot of making a standalone allocation runner for kind of debugging purposes, where you could just throw allocations directly at it. But anyway, now we're getting into the client side of things. But yeah, all clients care about is allocations.
Okay. Well, I think this is actually like a nice place to maybe wrap it up. Like we went all the way from job submission to the client can now grab the allocation and start
Yeah.
running it, which was quite far down the rabbit hole. Thank you so much for showing us around here. And
Yeah, my pleasure.
I hope everybody enjoyed the show. And please, if you have any requests for what we could show you next or what you're interested in, please let us know. And again, Michael, thank you. And with that, thank you, everyone. Bye.
Bye.